Hi, today we're going to learn how to do the derivatives of a lot more functions and only learn one new formula in order to do it. That sounds like a pretty good deal to me. So, let's take a look at the function that I've got written up here. Not a real complicated function, but is it one that we would know how to do? Well, not as it's written. We've never learned a formula for this, but if I were to cube it out, if I were to multiply x squared minus 1 times x squared minus 1, get a polynomial and multiply that times x squared minus 1, then we could actually do it. And it wouldn't even be that terrible. But think about this. This could easily be to the 30th power. You really wouldn't want to multiply that out that many times. It would take forever and you'd probably make some mistakes. So we're going to look for a different way that we could solve this problem and the other one, and they would be about equally easy to solve. Now, we don't want to just have to deal with all these separate functions. So we're going to try to come up with a more general rule that would work for many type functions that are like this. This is not the addition of two functions. It's not the multiplication of two functions, so we could use the product rule. It's not the division of two functions, so we could use the quotient rule. What it is, it's the composite of two functions. This is a composite function, and it's compositing the function f of x equals x cubed and g of x equals x squared minus 1. Now we could call this whole thing f of g of x. It's not cubing x, it's cubing g of x. And it's going to be important in the composite function which one is the main function. Well, since we're really cubing this other function, we would consider f to be the main function there. So in general, let's try to come up with a formula to take the derivative of any composite function. And that will just open up all kinds of avenues. So, the only way we have of taking the derivative of a function is our limit definition. So we have to take the limit as h approaches 0, and then we would have f of, normally it's f of x plus h minus f of x, but in this case it's f of g of x plus h minus f of g of x all over h. But if you don't mind, I'm just going to slide the h over here and consider this to be 1 and this to be 1. It's really the same thing. And I'm going to, instead of putting a 1 here and a 1 here, I'm going to put g of x plus h minus g of x here, and g of x plus h minus g of x here. It may look more complicated, but it's going to be doing something for us. And all I really did was multiply by 1, which is a legal thing to do. Now, I have the limit of this function times this function. Well, that's equal to the limit of the first function times the limit of the second function. This is a nice thing about limits. So I could go f of g of x plus h minus f of g of x over g of x plus h minus g of x, the limit of the first function times the limit of the second function. Now, here's where the good things happen. Right here, that's something we've looked at quite a bit. That's merely g prime of x. It's the other side that's a little more complicated. But if we draw a graph, I think it's going to help. If I just take a function, y equals f of g of x, and I take 2 points. Now, before we would call this x and this x plus h, but the function f is not working on x, it's working on values of g of x. So I'm going to call this g of x, and over here, g of x plus h. Now, if I take the slope of that dotted line, I get the rise over the run. Well, the rise would be f of g of x minus, or f of g of x plus h minus f of g of x, which is exactly what I have right here. F of g of x plus h minus f of g of x. So that's the rise. And then what's the run? The run is going from here to here. So that's g of x plus h minus g of x, which is exactly what shows up right here. So if I forget the limit, all of this is the slope of this dotted line. But what happens when I take the limit as h approaches 0? Then this dotted line becomes the slope here, which we've called the derivative. So what we see is all of this right here is just the derivative of f, but not at x, at g of x. And now we have just proved the formula. That now we can just bring this derivative down, and we see the derivative with respect to x of f of g of x, make sure that that's clear, is equal to this. And if I box that off, we have something that's going to be a really important formula. So I'm going to give it a name. The chain rule. Now, most books, if you look in it, will call it the chain rule. I've always called it the chain rule in my classes, and the students always felt that it works just a little bit better. So I'll let you make the choice what you want to call it. Let's just go back to this original problem. How would I take the derivative of that? Well, if we use this formula, we call this f of g of x. It says the answer, and we'll just do it down here, is going to be the derivative. And it says use the derivative formula for f. Well, f is the function x cubed. So the derivative is 3x squared. So we go 3x squared. Except it's not x. That's the thing about the formula. It's not f prime of x, it's f prime of g of x. Well, g of x is just x squared minus 1. So we just put in x squared minus 1, and the last part of the formula just says multiply that times the derivative of this other function. Well, g of x is x squared minus 1, so the derivative is 2x. And you're done. Now, the nice thing about that, what if this really had been to the 30th power? It wouldn't have been that much more difficult, because the derivative of x to the 30th would just be 30x to the 29th. And then you would just put in g of x and 2x, and that would be your answer. 60x times x squared minus 1 to the 29th power. That would be the derivative of that really complicated function. So this chain rule is going to be really helpful to us. So let's just look at 4 examples and using the chain rule and see, even though these functions look completely different, they're all going to be done pretty much the same way. Look for consistency. So here's the first one over here. Now, so we don't have to go back and forth, I've rewritten the chain rule down here. So the first thing we're going to have to do is recognize what kind of function it is. Is it a composite function? Well, if you look up here, this is not a multiplication, it's the sine of this other function. So we have 2 functions, the sine of x and x squared minus 4. And the main function, I hope you see, is the sine of x. You're taking the sine of this other function. So if we use the formula for the chain rule, what is f prime of x going to be? Well, let's look at it. It's the derivative of f. The derivative of the sine is the cosine. But it's not of x, it's of g of x. Well, g of x is x squared minus 4. And then the last part of the formula says multiply by g prime of x. Well, the derivative of x squared minus 4 is just 2x. And we've got f prime of x. Now this problem says to find f prime of 2. So we just have to plug in 2, and we get what? 2 times 2 is 4 times the cosine of 0. So the answer is 4. We have just found the slope of this function at x equals 2, the instantaneous rate of change. So that's our first use of the chain rule on a trigonometric function. Well, let's try another one. Y equals the cosine of pi over 2 minus 3x. Find dy dx. So we're finding the derivative. Again, we have a composite function. The cosine of x is one function, and the g of x function in here would be pi over 2 minus 3x. So that means dy dx, the derivative of the cosine is minus the sine. But it's not of x, it's of this g of x. So I put in g of x here, because that's what the formula says. G of x, pi over 2 minus 3x, and then I multiply by the derivative of g of x. Well, that's not too complicated. The derivative of a constant, pi over 2 is 0, and the derivative of minus 3x is minus 3. So that's our answer for dy dx. But they want to find it at x equals 0. So you could say dy dx, this is the way you could say that, at x equals 0, you'd have a minus times a minus is a plus 3. The sine of pi over 2 is 1. So now we've found the slope of this function at x equals 0. Do you see how we did those pretty much the same way, even though the functions look quite a bit different? Okay, we're going to end with 2 pretty tough problems. But I'm quite confident that you can follow it. This one, you've got g of x to be this function. Now, even though this sine squared of x is a nice shortcut way for saying the sine of x squared, that's what it really means, and sometimes it's really nice to have it written like this, but when you're doing derivatives, I highly recommend that you just think, even rewrite the sine squared of x to be the sine of x squared. Now, it is a composite function. One function is the sine of x, and the other function is x squared. But this time, the main function is the squaring function. You're not taking the sine of something, you're taking the sine of x and squaring it. So the main function is the squaring function. That's going to be your f. So, if I want to take g prime of x, constants, like always, we can just keep out front. But what's the derivative of x squared? It's 2x to the first power, which I don't have to write. But what's the function? It's not x, it's the sine of x. Now we've done the first part of the chain rule. The second part says to multiply by the derivative of this g function. So that's just going to be the derivative of the sine is the cosine. So altogether you get negative 10 sine of x cosine of x. And we've really solved the problem. We've found the derivative, but this one says to find the second derivative. So we just have to do this again. What is g double prime of x? Okay, this is actually really good review. This is no longer a composite function. It's the sine of x times the cosine of x. So what rule do we have to use? The product rule. So we just, again, bring our constant out front, and then what's the product rule? It says the sine, the first function, times the derivative of the cosine, which is minus the sine of x, plus the second function, the cosine of x, times the derivative of the second function. The derivative of the sine is, the derivative of the cosine is, let's see, the first times the derivative of the second, plus the second times the derivative of the sine is the cosine. So, the first function times the derivative of the second, plus the second function, the cosine, times the derivative of the sine, which is the cosine. And basically, that's your answer. To make it look a little bit nicer, you'd probably want to say cosine squared of x minus sine squared of x. That would just make it look a little bit nicer. So let's just try one last problem. I'm hoping you can see that this is a composite function. And the main function is the sine. It's the sine of where my hand is, this other function. So, actually, let's just make this y prime. We don't want to make this too long. We'll just take the first derivative of this. So, y prime of x. The derivative of the sine is the cosine. But it's not the cosine of x, it's the cosine of this other function. So I'm going to write that in a different color. Pi plus the tangent of 2x. And just to try to clarify things, I'm going to write it like that. But then, the second part of the chain rule says to multiply by g prime of x. So let's forget for a minute what we've done and just say, let's concentrate on what is the derivative of this other function in here. Well, the derivative of pi, a constant, is 0, but what's the derivative of the tangent of 2x? Again, it's not the tangent of x, it's the tangent of 2x. It's a composite function. The tangent of x and the function 2x. So, what we have to do is say the main function is the tangent. And the derivative of the tangent is secant squared. But it's the secant squared of 2x. So I have to put in 2x, but then I have to multiply by the derivative of 2x, because we have to finish that, and you get 2. So what we really did there, we did the chain rule a second time. That's why they call it the chain rule, because you can have a composite function made up of 3 functions or 4 functions. Now, normally they don't get that complicated, so don't be too concerned about that, but we did a really tough problem here. So, altogether, if I want to find y prime of 0, what am I going to get? Well, the tangent of 0 is 0, so you have the cosine of pi, which is -1. The secant of 0, it's 1 over the cosine of 0, which is 1. 1 times 1 is 1, so all of this just becomes 1 times 2. So the whole answer just comes out to be -2. Now that, if you can do a problem like that, you can take the derivative of most functions. So, practice is what's going to make us better at these, but once you learn how to do the chain rule, you're going to grow to love it because it's going to be so powerful and really not that difficult as long as you follow the rules. So, have a good day.